All right, welcome back. We're going to continue on with our discussion of lipids. In this hour, we're going to talk briefly about the fat-soluble vitamins, and then we're going to talk about terpenes, which are the other class, which is another in our class of lipids. Okay, so these are examples of fat-soluble vitamins. They're included in lipids because they're nonpolar. So I will warn you, some of these molecules actually have portions that would be called terpenes for reasons you'll be able to see shortly. In fact, all of them do. But they're included here just as fat-soluble vitamins, listed here as fat-soluble vitamins, so we can have a brief discussion about them. If you look at the functional groups present in each one, we are overwhelmed by hydrocarbon functionality and underwhelmed by polar groups. In each of these cases, we have one section that is somewhat polar, and then the rest of the molecule is nonpolar. And that means that these are each soluble in organic solvent, and they tend to be soluble in the deposits of triglycerides that are present in fat cells. You need each of these vitamins for normal metabolism and health, and you can actually synthesize vitamin D from cholesterol, but in many cases, various foods are supplemented with vitamin D for health purposes. But the fact that each of these is fat soluble means that they are stored not in the blood or serum, but they're stored inside fat cells, and so you can accumulate them. You do need to consume small amounts of these, but you don't need to eat them every day, because what you ate yesterday, vitamin A, gets stored in your fat cells and can be used as needed. That being said, if you eat too many of these, you can have some toxicity problems because they stay with you. In contrast, you can eat a lot of vitamin C, which is water soluble, and if you have too much of it, you just excrete it through the urine. So retinol is vitamin A. This is perhaps, if we're lucky in this class, I'll show you how we make vitamin D from cholesterol as a precursor, or from something similar to cholesterol. Vitamin E is an antioxidant. Look at that phenol. Its job is to intercept radicals. That proton can be abstracted, that hydrogen atom can be abstracted from any radicals, and the resulting radical phenol is resonance stabilized. Note the nonpolar tail that makes it fat soluble. Vitamin K regulates the synthesis of prothrombin and other proteins that are needed for blood clotting. Okay, so we'll spend the rest of our time in this chapter talking about terpenes, which are a very interesting class of biologically synthesized molecules with a fairly simple origin, but almost bewildering complexity. So just to introduce the subject, I'm going to show you several different terpenes. And in some cases, I'm ignoring the stereocenters. Limonene, which is a component of citrus oil. Related compound, again, I'm ignoring stereocenters, please forgive me. Menthol, which is the smell / taste of mint and is cool, has a cooling effect on the skin and on mucous tissues. Here's a linear compound with the same number of carbons. This is called citral and is an aldehyde component of lemongrass. And then here is another 5-carbon alcohol called geraniol, which is a component of rose oil. If that's not enough, this is a strange molecule that's called alpha-pinene, which is found in the oil of pine trees. If you want to see how this might look, actually, you could build a model, but something like this is a pretty good approximation. Notice that all of these have 10 carbons. All of these come from biosynthetically, so this is a biosynthetic retrosynthesis arrow. All of these come from the same precursor, which I'm going to draw now. This is called geranyl pyrophosphate. And geranyl pyrophosphate has as a key structural feature the pyrophosphate group, which you can think of as an excellent leaving group. And you'll learn more about that in biochemistry. And notice that the excellent leaving group is at, importantly, an allylic carbon. So you might expect the chemistry of geranyl pyrophosphate to be dominated by SN1 type chemistry, with the pyrophosphate leaving group leaving to give a resonance stabilized allylic carbocation intermediate. And then you might expect some of the other things to happen to lead to some of these products. For example, how would we get from geranyl pyrophosphate to geraniol? Well, the pyrophosphate leaving group could leave to give a resonance stabilized carbocation, and then water could attack that carbocation at the allylic carbon to give you this alcohol. And then that resulting alcohol could get oxidized by some biosynthetic mechanism to give you the resulting aldehyde. Key to understanding terpenes is to relate the structure of what I'm going to call a linear precursor, geranyl pyrophosphate, with the structure of the final terpene compound. And I want you to notice the regular spacing of branching methyl groups in the linear precursor. It turns out that terpenes are composed of what I will call regular 5-carbon units, which I'm going to label now, starting with the color purple. 1, 2, 3, branching methyl group 4, 5. I know I'm not following IUPAC rules for numbering things, and I don't care. 1, 2, 3, 4, 5. Then there's a bond between 5 and carbon 1 of the next isoprene unit, 1, 2, 3, 4, 5, or carbon 1 of the next section of our terpene, 1, 2, 3, 4, 5. So terpenes are composed of these individual 5-carbon units with a branching methyl group. We call that an isoprene unit, just as this green one is also an isoprene unit. Isoprene units are so named because of the parent compound isoprene, which I guess we could draw like this. And you will find this basic structure, a 5-carbon unit, one, two, three, four, five, where 3 is a branching methyl group branching off of 2. As a key feature of isoprenes. And so the branching methyl group is important because it helps you identify portions of a terpene and which isoprene units they came from. The other thing to realize about terpenes and this linear precursor, geranyl pyrophosphate, is that terpenes have directionality. You have a leaving group head, and then you have a dimethyl tail. And often you can find that dimethyl tail in some of the products that are downstream from this linear precursor. So, for example, let's show you how to do that. In menthol, can you find the dimethyl tail? Take a minute and see if you find it. Do you find 1 carbon bonded to 2 methyl groups? That should be right here. So that means that these 2 carbons here in menthol correspond to carbons 1, 2, and 3 of geranyl pyrophosphate. Do you see we're using some of the tools of retrosynthesis to sort of think about things this way? And then that means the next carbon has to be purple carbon 4. Which one do I think is purple carbon 5? Well, it turns out I can't tell. If I let it be this one, then this next bond is the bond between the purple isoprene unit and the green isoprene unit. This would be green 1, 2, 3, and there the branching methyl group is in the right place. 1, 2, 3, 4, 5. I might have chosen to do it the other way as well, and that answer would have been correct too. So those are the 2 isoprene units in menthol. The other thing you can do now, having identified the isoprene units in menthol, is to be able to say which of the bonds in menthol were present in the original linear precursor and which had to be made later. This bond between purple 5 and green 1 is what I'm going to call a typical head to tail bond, a head to tail sigma bond that is present in the linear precursor. In other words, when we went from this linear geranyl pyrophosphate precursor to menthol, we didn't have to make that bond. But then we can find bonds that are new that we would have had to make. I'll label those in blue. The linear precursor doesn't have a bond between purple 4 and green 5. So that bond between purple 4 and green 5 is new. That's a bond we had to have made in the process. Also, the OH group wasn't there. Also, there's some double bonds missing. When identifying isoprene units in terpenes, look for the branching methyl groups, ignore the oxygens, and ignore the double bonds. So we can use similar arguments to find the 2 isoprene units in limonene. Again, 1, 2, 3, 4, 5. where this bond between purple 5 and green 1 is present in the linear precursor, but this bond between green 5 and purple 4 is new. So if we were to propose a mechanism for how limonene is synthesized, we're going to have to account for that new sigma bond. Of course, we can use similar arguments for citral and geraniol. It's not hard. I won't label the individual atoms or bonds. I will just highlight the isoprene units. Okay. Alpha pinene is somewhat more difficult, at least at first glance. But we can do this either from this drawing or this drawing. I'm going to go with the one below. Start by identifying the dimethyl tail, and that's purple atoms 1, 2, and 3 respectively. Now I've got a choice as to where I should put atom 4. If I put atom 4 here, that puts the branching methyl group in the wrong place. So probably atom 4 is this one. 1, 2, 3, 4, then purple 5. That would make this a bond between purple 5 and green 1. One, 2, branching methyl group 3, 4, 5. And then that would allow me to identify bonds in the alpha pinene product that were not present in the starting material. This bond between purple, I don't really like where I drew that bond. Can I try again? This bond between purple 4 and green 5 we would have had to make, and then in the back this bond between green 1 and purple 2 we would have had to make. Of course, I can also highlight this and superimpose it on the overhead view. 1, 2, 3, 4, 5. There's the bond between purple 5 and green 1 that was present in the linear precursor. 1, 2, 3. Oops. 1, 2, 3, 4, 5. There's the second isoprene unit where this bond and this one are new. And so any mechanism would have to account for the formation of those new bonds. Why are we going through this in such detail? Because the natural products that you can get from these kinds of linear precursors are beautiful and complicated, but they come from simple linear precursors, and you can learn how to draw a reasonable mechanism for how that might be formed. I'll take you through this for limonene and ultimately alpha pinene. I want you to be able to identify isoprene units in terpene compounds. I also want you to be able to identify bonds that were not present in the linear precursors. And given a mechanism, I want you to be able to describe whether the steps in that mechanism actually lead to the product shown. Okay. So, I should point out that all of these 10 carbon pieces are called monoterpenes, even though they have 2 isoprene units. So a diterpene would have 4 isoprene units. A sesquiterpene would have 3 isoprene units, and so on. All right. Let me show you how geranyl pyrophosphate can be converted into limonene. And to some extent, if you think retrosynthetically and think about the new bonds that are present in the product that are not present in the starting material, you've almost solved the problem. So remember, geranyl pyrophosphate has an allylic leaving group. It's primed and ready for SN1 type chemistry. I've got the 5 in the wrong place in my isoprene unit there. Sorry. Okay, so notice that allylic carbon 5 in the geranyl pyrophosphate precursor is involved in a new bond with carbon 4. That's begging me to have the leaving group on carbon 5 leave to give a carbocation. Okay, so let's draw what would happen if the leaving group left. You're not used to thinking about primary leaving groups leave, but remember, it's not a primary, the product is not a primary carbocation here, it is a resonance stabilized carbocation. Which, of course, if I wanted to, I could draw this resonance structure just to illustrate that it is indeed a resonance stabilized carbocation. All right, so where I end up gives me the sense that carbon 4 on the purple isoprene unit needs to attack carbon 5 on the green isoprene unit. And I'm just going to label 4 and 5. So the question I should ask myself is, on carbon 4, do I have something that could be a nucleophile? The answer is yes. I've got a pi bond, and I've had pi bonds act as nucleophiles before. Is there an electrophile on carbon 5? Yes, the carbocation. Is it reasonable for a pi bond as an electrophile to attack a positive charge? Well, I haven't necessarily seen something exactly like that before, but it sounds similar enough to stuff that we've done in SN1 and in Chapter 10, Chemistry of Alkenes, that I'm willing to give it a try. I'll highlight in red the bond again that's already there. A question we should ask, though, is can carbon 4 reach carbon 5? So let me try to redraw the molecule, the carbocation, in a slightly different way. This is that bond in red. And the answer is that as we currently are, no, we can't reach purple 4, can't reach green 5. Because green 5 is held trans to green 1. Now, I often have students ask, well, what about this resonance structure where you've got a single bond between green 2 and 4? Can't I rotate around that single bond? And the answer is not without breaking the conjugation and turning this into a primary carbocation. So nature has a strategy for dealing with this. You don't necessarily want to know it, but I'm going to show it to you anyway. What will happen in nature, and maybe just for fun, I'll redraw the resonance structure here as well. You can't rotate, as I said, about the bond between 2 and 4 without breaking the conjugation and turning the carbocation from resonance stabilized to localized. But in nature, what's thought to happen is the pyrophosphate group that left, which I'm going to abbreviate as the OPP, in this case, now with 4 negative charges group, comes in and attacks at the more substituted carbon 2 to give me the following intermediate. By putting that leaving group back at carbon 2, I no longer need conjugation, and I'm allowed freely to rotate around the bond between carbons, green carbon 2 and 4. And so by rotation around a carbon-carbon bond, I can get into this conformation, whereupon if the leaving group leaves again, I now have a carbocation that's got a resonance stabilized carbocation that has green carbon 5 in the right place, close in space to purple carbon 4. And of course, we can draw a resonance structure of this intermediate. Some of that seems convoluted, and all of it you could have avoided if I were simply to allow you to rotate around the bond between 2 and 4. But there is evidence that nature actually does it this way. Now carbon 5 has the positive charge on it, and now we're poised for an intramolecular nucleophile attacks electrophile reaction. And you should be able to predict what happens next based on what you learned in chemistry 351. When an alkene attacks, which of the two carbons, purple 2 or 4, is going to get the new bond with green 5? It should be 4, because the product is going to be a carbocation. We want the new bond with 4 so that the positive charge can end up on more substituted carbon 2. And this is the other beautiful thing about terpene chemistry. Those branching methyl groups create intrinsic regioselective preferences that guide the connectivity of the reaction. It has to be carbon 4 that makes the new bond purple 4, that makes the new bond with green 5. It has to be that way so that the positive charge can end up on more substituted carbon 2 where it's more stable. And I'm sorry, I labeled the bond between purple and green isoprene units incorrectly there for a moment. Okay, now look at my target. I want limonene. You tell me how I get limonene. Look at the difference between what I drew here, we just made that new bond, and limonene. The difference is the pi bond between 2 and 3. Look at that intermediate. How am I going to get a pi bond between 2 and 3? And the answer is, it's simple. Do an E1 style elimination reaction. So this is another example of the kind of chemistry that terpenes can do. You've seen SN1 style leaving group leaving. You've seen pi bond attacks carbocation, which should look like chapter 10 addition of electrophiles to alkenes. And then this E1 style elimination where some base provided by the enzyme removes the proton, and that gets us to our limonene product. Okay, so that's one example how if you pay attention to what bonds are new in the terpene product versus the linear precursor, you can propose a mechanism that makes a lot of sense. This is fun. Let's do more. So I told you about alpha pinene, which we'll copy in both of these structures. Notice that in alpha-pinene, we have the new bonds that we need to make. Let me label the carbons again. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. The new sigma bonds we need to make are between green 1 and purple 2. And we also need a new sigma bond between green 5 and purple 4. Now, if you're paying attention, notice we already made the bond between green 5 and purple 4 in limonene. That tells me that this precursor with the carbocation on carbon 2 and the newly made bond between green 5 and purple 4 is an intermediate on the way, a common intermediate on the way to alpha-pinene, a common intermediate in the pathway to limonene versus alpha-pinene. How does an organism know to make alpha-pinene versus limonene? Of course, enzymes can guide the process, also the needs of the organism. We're not necessarily talking about that. We just want to propose a reasonable mechanism. So if I take this carbocation, this common intermediate, the one that already has the bond between purple 4 and green 5, I can start to ask, how do I get the other bond? And recall, the other bond is between Did I do that wrong? Well, let's continue on. I need a bond between what I thought was okay. I'm just thinking through what we need to do to have this make sense. I told you earlier that sometimes we were going to have a choice in deciding where the isoprene units were, 1, 2, 3, 4, 5 versus 1, 2, 3, 4, and 5 on this side. Sometimes we may need to revise our assignment of isoprene units based on the mechanism. In any case, as I look here, I know I need to make a bond. And it looks like it involves green 1 and purple 2. Purple 2, I've got good news. Purple 2 has a positive charge on green 1. Or sorry, purple 2 has a positive charge. Purple 2 is electrophilic, so that's good. The problem is on carbon 1, I don't have a nucleophile. That may be okay. Depending on how things go. Let's instead, I do have a nucleophile involving green 2 and 4. And so let's imagine that nucleophile between green 2 and 4 reaching over and doing an intramolecular reaction, an intramolecular attack of the pi electrons from 2 and 4 onto purple 2. We're going to see, again, we would predict regioselective alkene addition of an electrophile to an alkene. we expect the new sigma bond on carbon 4 so that the positive charge can be on green carbon 2. From our perspective, this is going to be the molecule puckers and the pi bond reaches across underneath the face of the molecule to attack the positively charged carbon 2. If we were to draw this, what would this look like? Probably something like this. So here is, according to my isoprene unit of drawing things, according to how I've assigned the isoprene units. Here is the new bond we just made between green 4 and purple 2. Here in blue. And then to be consistent with what we've drawn previously, here's the bond between purple 5 and green 1, which was there in the linear precursor. And here is the bond between purple 4 and green 5 that we previously made. Okay, so it looks like I just made a new sigma bond between green 4 and purple 2. Is that okay? Is there still a way to get to my desired product? The answer is yes, because in my desired product, I need a double bond here. And I have a positive charge there. So it's reasonable to imagine that a base can do an E1 style elimination step to get me my desired product. I'll go ahead and label things as I've done previously. In red is the bond from the linear precursor between purple 5 and green 1. In blue are the bonds between green 5 and purple 4 that we made from that common intermediate, and then green 4 and purple 2 that we made in the most recent step. And there's alpha pinene. That's a reasonable mechanism. We did, from the common intermediate, we did a pi electrons attack a carbocation to make a new bond. Now notice that based on my mechanism, I actually have assigned isoprene units differently in my product of alpha pinene than I anticipated in the beginning. Over here, I assign 1, 2, 3, 4, and then going around the ring from this perspective clockwise to 5. Over here, I temporarily assigned it 1, 2, 3, 4, and then counterclockwise to 5. You will sometimes make those kinds of mistakes in identifying isoprene units. You will sometimes have a choice of, do I go clockwise versus counterclockwise around the ring? try to use the position of the methyl group as a key, but notice here that it works if I go 1, 2, 3, 4 counterclockwise 5, then 1, 2, 3, 4, 5 in green. It also works if I go purple 1, 2, 3, 4 clockwise 5, then green 1, 2, 3, 4, and 5. So you will sometimes find two equivalent ways to assign isoprene units. I will never put you in a situation where that choice has any point value associated with it, so you won't have to worry about that. But it may cause you may need to, if you get started one way and then learn as you do the mechanism that it probably was the other way, that's fine. You can use those insights along the way. Okay? The point is to use your intuition about where isoprene units are and the kinds of reactions that these molecules can undergo to give you an idea of where the new bonds come from. All right. Sorry about the pause in the middle of that. I noticed that difference as we were looking at it. If that discussion's confusing to you, you may need to pause and go back and watch that last little bit again to confirm what I was talking about. To briefly summarize, sometimes you will have a choice in two different ways to assign isoprene units, and one will be more reasonable in terms of coming up with a mechanism that explains the connectivity in the product. This way of assigning isoprene units in alpha-pinene is fine. This way is also fine. This way works best with the mechanism, but I'm never going to give you this and this, for example, as options A and B on a test and have one be right and the other be wrong. Okay. I'm also not likely to show you both of them and require you to select both of them as correct. That would be mean. Okay. A couple of more things we want to do. I want to show you an even more complicated terpene. This is a sesquiterpene. Again, we're going to go through it. We're going to identify the isoprene units. We're going to compare it to its linear precursor, and then we're going to see if we can propose a reasonable mechanism. Going to love this. 2 5-membered rings. One of them's fused to a 6-membered ring. And there's an OH. This is called cedarol, and it's isolated from the cedar tree. And its linear precursor is this sesquiterpene called farnesyl pyrophosphate. Here are the terpene units. 1, 2, 3, 4, 5. I'm sorry, I should have put double bonds there, there, and there. Here's a bond between purple 5 and green 1. 1, 2, 3, 4, 5. I'm not going to label all the atoms. Another bond between purple 5 and the next isoprene unit. Let's make it orange. And there should also have been a double bond there. A bond between green 5 and orange 1. And then orange 5 has the allylic leaving group on it. So chemistry here is going to be very much the same as we saw in the geranyl pyrophosphate linear precursor. That is, we expect the leaving group to leave to give us an allylic carbocation, and then we're going to go from there. Let's now look at the cedarol and see if we can come up with at least one reasonable way to identify isoprene units. And first, we're going to look for the purple dimethyl tail. So find the dimethyl tail and you will have identified carbons 1, 2, and 3 from your original linear precursor. 1, 2, and 3. All right. Now we have to decide where to go, and we may have a choice to make. 1, 2, 3. Should this be carbon 4 or should this be carbon 4? If this is carbon 4, then I worry about which carbon 5 is. It can't be this one because carbon 5 never has a branching methyl group. If I go this way, that could work. Then this would be green carbon 1, 2, 3, 4, and 5. But then I have to explain where this isoprene unit came from. And 5 needs to be bonded to orange 1. So that strategy doesn't work. What if instead I decide to put purple 4 here and 5 here? 1, 2, 3, 4, 5. That creates a bond between purple. That means that the indicated red bond is the one between purple 5 and green 1. 1, 2, 3, 4. So far, so good. At this point, I have a question about whether this should be 5 or this should be 5. If it's the upper one, that would be 1, 2, 3 branching methyl group 4, 5. Oops, I can't count. 4, 5. That would tend to work out and has the branching methyl group in the right place. Let's see if it works if we go the other way around the ring. 1, 2, 3, 4, 5. Then this would be orange 1, 2, branching methyl group 3, 4, and 5. So this is a case where I'm not sure. And there's no actually way for me to know unless I go in and do some experiments to try to figure out how biology actually makes this. What I'm trying to do is to come up, what my goal is for you to come up with a reasonable mechanism based on these simple SN1 and E1 and alkene addition type steps to get this complicated reactivity pattern. So whether we should number clockwise or counterclockwise around this 6-membered ring isn't actually going to matter. I'm going to just choose one way. We'll work on the mechanism. We'll see if it works. If we need to revise, we can. I know you're uncomfortable with that. I know you would like to be told a flow chart for how to make the right decision without making any mistakes, but frankly, that's not the world that we live in. Sometimes you have to come up with a hypothesis, try it out, experiment on the word as it were, and then revise your hypothesis as needed. So carbons 1, 2, 3, 4, and 5, red bond between purple 5 and green 1. Carbons green 1, 2, 3, 4, 5, red bond between 5 and 1. The red bonds are present in the linear precursor. Then let's identify the bonds between isoprene units that we need to explain. These are the ones that are not head to tail 5 to 1 bonds. So that would be the bond between purple 2 and green 4. That would be the bond between purple 4 and green 4, and the bond between green 4 and orange 5. Those are all bonds that I'm going to have to make as I synthesize this molecule. So we can think of some ways to do this. Let's just write down a list of the sigma bonds that I need to make. I need to make one between purple 2 and orange 4. I need to make one between purple 4 and green 4. And I need to make one between green 4, and orange 5. So let's see how many of these we can do. I won't draw all of the steps. We're going to talk through some of them. What I'm going to draw for you now is an intermediate that you could get following some very similar steps as we saw previously in the limonene synthesis. So again, I'm skipping ahead. We would have the pyrophosphate leaving group leave first to give you a resonance stabilized carbocation. Then, as we did earlier, the pyrophosphate group's going to hop back on the tertiary carbon so that we can rotate around the bond between 2 and 4 to get carbons 4 and 5 in the right spot. Then the leaving group leaves again to give us this carbocation. Only this time, because we're dealing with a 3 isoprene unit starting material, it's orange 5 that the carbocation is on. Okay, and you may want to pause and see if you can draw the arrows to get from here to here based on what we've done previously. Now, my list of data tells me my list of new sigma bonds to make tells me I need a new bond between orange 5 and green 4. Well, perfect. 4 is part of a double bond, and 5 is a carbocation, so I can do the regioselective addition of an electrophile to an alkene. The bond is between green 4 and orange 5, so that the positive charge can be on more substituted green 2, where it is more stable. All right. Again, it may help me to number, 1, 2, 3, 4, 5, and then the methyl groups 1, 2, 3, 4, and 5. Okay, so check. I've got my first of the 3 sigma bonds I need to make. The next shows that I have a bond between purple 4 and orange 4, or sorry, purple 4 and green 4. And that's a problem because right now, green 4 doesn't have a positive charge. Purple 4 is part of an alkene, but I don't have an electrophile on green 4. How can I do that? And this introduces the, I think, newest of the reactions that you can see in terpene chemistry, and that is carbocation rearrangement. So let me show you how this is done. You have a tertiary carbon 2. If we do a 1,2 hydride shift, that will move the hydrogen, the CH bond, over to green carbon 2, and that will leave a positive charge on green 4. Now, some of you are going to say, I thought you told us only to worry about carbocation rearrangement when a secondary carbocation could rearrange to a more stable tertiary carbocation. That's true. I did that from a predict the products perspective, but this is a mechanism perspective. And in the case of mechanisms, you need to, given a result, you need to be prepared to use a 1,2 hydride or alkyl shift to explain a result. The result is we have a sigma bond between purple 4 and green 4. We can't get it in any other way than if we do a 1,2 hydride shift to move the carbocation onto carbon 4. At this stage, I'm going to redraw the tail of the purple isoprene unit briefly to get it in the right spot. 5, 4, 4, oops, that's an eraser. 5, 4, 3, 2, 1. Here's the purple isoprene unit. Now carbon 4 is in the right place to do another regioselective addition of an electrophile to an alkene, and that's going to make a ring involving green 4, green 2, green 1, purple 5, and purple 4, a 1, 2, 3, 4, 5 membered ring. I realize that this is going a little bit longer than expected. I'm going to just continue onward so that we can finish the story rather than delay it to a subsequent recording. You're welcome to pause now and take whatever break you need before proceeding. I know a lot of you are listening to this on 1.5 speed anyway, though, so it probably isn't that big of a deal. I screwed up. Oops, keep getting the eraser. Okay, and there's the purple isoprene unit. 1, 2, 3, 4, and 5. Reviewing what we've done now, we had previously made the bond between purple 4 and 5. We just barely made the bond between we previously made the bond between green 4 and orange 5. We just barely made the bond between purple 4 and green 4. That leaves us, that's another regioselective addition of an electrophile to an alkene following the Markovnikov rule. The positive charge ends up on the more substituted carbon where it's more stable. That checks off our second of our 3 bonds that we need to make. The last bond we need to make is between carbons 2 and 4. Between purple 2 and orange 4. Purple 2 has a positive charge on it, so purple 2 can be the electrophile. Orange 4 is involved in a pi bond, so that can be the nucleophile, and we could expect another regioselective addition of an electrophile to an alkene to make a new sigma bond between orange 4 and purple 2. We would expect the new bond to be with 4 so that the positive charge could be on carbon 2. Let's draw that happening. Pi electrons attack positive charge on carbon 2. This may be somewhat difficult to draw. The best way to do it, though, at this stage is just to draw the bond between the right atoms and not worry about getting the geometry right. So, we erased the orange. Let me put that back. The new bond is going to be between orange 4 and orange 4 and purple 2, so let's just draw it there. That's not a very lovely straight line, but that will do for now. And the positive charge should be on carbon 2. At this stage, we have basically accomplished what we need to accomplish. What we just made was another 1, 2, 3, 4, 5-membered ring. We now have a positive charge on orange 2. Look at where the OH ends up in the product on orange 2. So it would seem reasonable, and this is maybe the 5th of our reactions that we know how to do on positive charges, to have water attack the carbocation of this intermediate to give the corresponding alcohol. This is basically an SN1 type reaction, and then the resulting OH2 plus oxonium ion would get deprotonated by a base to give you the alcohol cedarol. It's probably worth just a little bit of time to convince yourself that what we have drawn here is indeed this starting material. Notice how few steps were needed to get from this simple linear precursor to this more complicated structure. And notice how all of the reactions involved regioselective addition of an electrophile to an alkene with Markovnikov selectivity, or carbocation rearrangement, or nucleophile attacks positive charge. Hopefully I've shown you that you can use basic 351 type reactions and these lovely linear terpene precursors to get molecules of beautiful complexity. And that's where we'll need to stop for today's lecture.